Hello everyone! Today we're going to learn the basics of quantum physics. So, for those of you who don't know, quantum mechanics is basically the science of the really small. So, particles, basically particles. And today it's Quantum Mechanics 101. So we're going to have to work with some fundamental particles. These particles are included in the standard model of particle physics. Don't worry, it's not as complicated as it looks. So first up, quarks. Quarks come in 3 generations with 2 types in each generation. In the first generation, there's the up and down quarks. In the second generation, there's the charm and strange quarks. And in the third generation, there's the top and bottom quarks. These quarks join together to form hadrons, which are just combinations of quarks. And in these hadrons, there are baryons, which have 3 quarks, and mesons, which have 2 quarks. There's a complex system when joining these quarks together, which I'll go into in another video. But basically baryons are the particles that are more known, like neutrons, protons. So next we have leptons. Leptons also come in 3 generations with 2 types, although you can also look at them like the same particle with 3 types. So we've got first the electron, which we all know basically, and then there's the big brother of the electron, the muon, or the mu electron. And then there's the big brother of the electron, the tauon, or tau electron. And those are all the basically types of electrons, really generations. And now we've got the neutrino. Neutrinos are really evasive particles that right now trillions of them are raining down on you from lots of different sources, but barely a single one interacts with you in your whole lifetime. So yeah, they barely interact. And there are also 3 generations: the neutrino, the mu neutrino, and the tau neutrino. So you may notice like another half of the table, and that half is the antiparticles of the particles I've just mentioned. So for the muon, the anti-muon. For the charm quark, the anti-charm quark. So it's just antimatter, basically. And finally, we have bosons. Bosons are the carriers of force. So for example, the gluon carries the strong force, which, spoiler, is what joins quarks together. The photon carries the electromagnetic force, which is basically light and magnetism. Then the W and Z bosons carry the weak force, which has some other effect that I'll talk about in another video. And finally, the Higgs boson is basically what gives particles mass. And all of these particles, the interactions between them, basically everything in the quantum realm is driven by probability. This has a few implications that we'll talk about now. So every particle has something called a wave function. A wave function is like a probabilistic wave that represents where a particle is or its energy, but usually it's its location, especially to laugh about the unintuitiveness of quantum mechanics, and we'll see why now. So let's represent it here. So we've got a box here with an electron, perfectly normal. Well, no, because actually this electron isn't here. This electron is a wave function that goes all the way here and has this probability to be here in the center, but this probability to be here or here. It has basically a wave function. This is in 2D so that we can visualize it, but it would be like in 3D, a weird thing. So it's got its wave function. So imagine you measure the electron and you find it's here, for example. Or you measure it again and you find it's here. So it'll tend to be near the center of its wave function, in this case the center of the box, but there's a little portion of its wave function here, which means that if you measure the electron, it can end up here. That actually happens. It's actually why we can't make computers smaller, because transistors are getting so small that electrons are literally teleporting into another place, basically. This is called quantum tunneling, and it's also because of the wave function. Another way quantum mechanics can mess up our lives even more is through something like this Schrodinger's cat paradox. You may have heard of it, but here is like the setup of the paradox. So if you've got a cat in a box with a quantum device that has a 50-50 chance of delivering a poison into the box. But that means that as long as you don't measure it, that's why it's all inside a box, and this would be the observer. So as long as the observer doesn't measure it, this is all inside a wave function. That it started with this atom, for example, decayed or not decayed, that can trigger the release of the poison, and so the cat can be alive or dead. So the whole wave function represents the cat alive or dead. But that means that as long as you don't measure it, the cat is alive and dead at the same time. And if you ask me, that's pretty paradoxical. And how do we represent all this mess? How do we calculate it? Well, with Feynman diagrams. These are simplified ways to let us know how particles can interact. For example, here, two electrons are repelling each other. You can see in the arrows, you can see the direction of the electrons. But to interact, as I told you, the photons are the carriers of the electromagnetic force, and that includes magnetism. So when they get close to each other, a virtual photon, which is just a photon that appears and disappears out of nothing, yeah, that also happens, really weird, lets the electrons interact so that they can repel. You can also see that in the lines in the diagram. Well, I mean, it's comparatively quite simple, right? Well, no, because as long as you don't measure every single point in the path of the particles, they're actually taking every single path there can be in the universe, not even limited by the laws of physics. So literally, an electron, just to interact with another electron to repel, it can surpass its event horizon, go to one edge of the universe, then come back to the other, then take a walk by the sun's surface, come back, and then interact. And it actually does that, as long as you don't measure it, because it's a wave function of every single path there can be. So literally, Feynman diagrams have infinite possibilities. And actually, it doesn't take a random path out of all of those. It takes all the paths at the same time, and if you don't measure them, you can't know which one it took. Because, well, really it's a wave function, so it didn't take a single one. It's extremely counterintuitive. And not only does that work for paths, because also a particle can turn into a particle and an antiparticle, which annihilate, and then turn into another particle, which also divides, and then they annihilate, and it turns into another particle, and it can do that infinitely many times. I wouldn't even notice because we're not measuring it. So it's crazy. So I wouldn't blame you if your head just exploded. If it didn't, you could use what you have left to just click those like and subscribe buttons. And of course there are a bunch of things left to explain from quantum mechanics, but those deserve their own videos. So you probably noticed I've got a little microphone here, and I got it for my birthday, and I hope it will increase the audio quality of my videos, and so that you can hear me better. So tell me in the comments what you think about it. I'll see you in the next video. Bye!